Good morning. As we get more and more participants to join up, I know class doesn't start technically for another minute, but make sure you're taking your attendance link in the bottom left. There's a QR code. If you have a second device handy, like a cell phone, you can scan that QR code. As you're working on the bell ringer, I'm going to give you a hint. There are 4 types of discontinuities that occur. There are 4, rather, discontinuities that occur on these 2 problems combined. That's a hint as you try to solve those. If you want to use a graphing calculator to help you out, here's Desmos. It's a free option. If you scan the QR code, it should pull up those 2 equations already graphed for you. You can look for them that way. But make sure you've taken attendance. We'll get going in just a moment.
The time is 9:15. It is now the beginning of the 5th period.
Well, there you heard it. The announcements are back on here at Skyline. It's the beginning of 5th period. Make sure you get your 2 bell ringers done. You have 5 minutes to try to work on these 2 problems. So the most important thing, though, is you would take your attendance, fill out that link, and then begin working on that bell ringer. Again, you're looking for 4 types or 4 discontinuities between those 2 graphs combined. While I'm giving you time to work, is there anyone right now who's on a cell phone only because you couldn't get your Chromebook to work properly? So I'm taking the silence that everybody right now is on a Chromebook. All 14 participants currently are on a Chromebook device.
I am.
Perfect. You have 3 more minutes for the bell ringer. Currently, there's 5 people who are online who have not taken attendance. Make sure you get that taken, please. If you can't scan a QR code with any other device, you can go through PowerSchool Learning, our digital classroom. Two more minutes. I sent out a few messages also. If you're a sophomore or junior and were absent one of the days they did MAPS testing, and you're missing either your reading test, your math test, please send me a message so I can get you the emails to the correct individual so you can take those 2 tests. Tomorrow is your last day to get those done. So if you were absent and you were a sophomore or junior, seniors did not take them, but sophomores and juniors online right now, if you were absent for one of the MAPS tests, either the reading or the math, please let me know so we can get you to take those exams. All right, just a few more seconds. All right, I've got 9:20, and currently I have all 20 of you signed in. That's great, and on the attendance link. So I'm just going to go over a few things with you, just in case you're new and transferred over, or just watching this video later to help yourself out. On the bell ringers, what I always have is a QR code for your attendance. Now that's great if you're on a Chromebook and you have a secondary device available that's able to scan this. But if you don't, I'm going to walk you through how to get to that attendance link. So I'm going to go to our digital classroom that we're using for pre-calculus, and that's my Power School Learning. Again, if you don't have the site bookmark, like I've encouraged you to do so, you go to clever.com, and what I suggest is going ahead and typing in this /in, like you're in Dallas Independent School District. So the word in /Dallas ISD. If you do that, it'll pull up this site here. We log in with Google. Make sure you choose your ID number at dallasisd.org. If it's not an option to you, just hit use another account and add it. Once Clever loads, look for the Power School. It'll be under the featured. You can favorite it to move it up to the top like I have. Click that. Now, yours is going to start looking a little bit different on this screen. It's because yours will have Power School for parent, but there's an extra little button on the right that'll say sign in as a student, and that's what you're going to hit. And so from there, our screens will look a little bit different, but when mine loads, I see attendance. This is where I take attendance for all my pre-calculus. For you, you will see your class is listed kind of in the middle of the screen. On the left, you'll see, I believe, if my order's right, your attendance, and on the right, you'll see grades. But either way, what is consistent on both your side and my side is that we have this blue ribbon going across the top. That first button on the far right side of the screen is called the Applications button. If you click that, you can choose Power School Learning, and this gets you to your website. And so once in here, you might, I don't know how many of your teachers are using Power School Learning, but any teacher that's activated a class this way, you will have available to you on this left side. So we're 5th period right now, so I'm going to click your class. Once you get here, this is what I suggest you bookmark by just starring the page. Hit star, save the bookmark. This is your home page. And so now that's the first thing to do is how to get to Power School Learning. I just walked you through right there. Now, secondly, some people have been having a lot of troubles getting logged in on Zoom on their Chromebooks. The Chromebooks are difficult because you cannot actually download the Zoom app. It all goes to the web page. So anytime we have a Zoom error, it has to do with how you're logged in on the web page. So if you click this link and it's not working for you, like right now, if you're listening to me and you're on your cell phone just because your Chromebook's not working, let me problem solve for you. If you go to the 4th bullet, I made a YouTube video of everything I'm about to say to walk you through so you can like pause it, rewind it, and hit all your stuff. But that video right there will help fix your Zoom errors. But here, I'm just going to talk you through it. If that link's not working for you in Chromebook, what you need to do is open a new tab and go to zoom.us. That's Zoom's homepage. When you're here, you're going to look in the top right-hand side of the screen where it says sign in. The sign in button is right next to that orange button. When you hit sign in, it's imperative that you do not try to sign in to here to Zoom. I think that's where most students are having their errors. You have a Zoom account, you sign in there, but that won't work for my class. I try to add security just because if you paid attention to the news, Zoom, some people have said, is not the most secure. And so this is a way we can secure it, is forcing you to sign in through Google. And so that's what I'm doing. You scroll down, sign in with Google. And again, I want you to choose your ID number at dallasisd.org. So by this time, if you've just gone through Clever, it should already be there, but in case it's not, just use another account and add it. But you're looking for your ID number at dallasisd.org. Obviously, mine's a little different, but I'm a staff member, not a student. That's why mine's a little different, but that's what I'm going to choose here. And it's going to come to this screen. Now, the easiest thing for some students now is if you go back to that previous tab, the PowerSchool Learning website, now you can try the tab, but for some, it's still, for some reason, not working. So here's the answer that will solve the problem for everybody. If you just copy the meeting ID, you just select that and copy it. I just right-clicked and copied, and take it back over to My Meetings over here. When this loads on yours, you won't see these pre-cal meetings. These are my reoccurring. Yours is going to be blank there, but the rest of the page is going to look the same. Just go again to the top right and hit Join a Meeting. When you hit that Join a Meeting, this is where you paste that meeting ID, and when you log in through here through the browser, there shouldn't be any more issues. It should log you in with your DISD account. It'll ask for a password, but again, the password's listed right below in PowerSchool Learning. In this case, the password is fifth. And so you'd hit join, it would ask for password, and that's how you can join up on a Chromebook if you've been having Chromebook issues. I know if you have a different type of computer other than Chromebook, you probably have not had the problems, because if you download the app, it solves your problems, but Chromebook doesn't allow you to download the Zoom app. So that's where the problem is, and that's the quick fix. So having said that, what are we doing today? I'm going to go over here to Chapter 1. We're looking at Chapter 1, Lesson 5. And so here's the new layout that I sent a message about yesterday and this morning is to check out for 1.5. Our lesson is parent functions and their transformations. What you're going to learn today is you're going to be able to graph and transform functions in this form here. This is a mathematical form where each letter A, B, C, and D have to deal with transformations. And so you're going to learn what is a number in the front that multiplies due to it. How does it transform a function? What about a value multiplying the x on the inside? What does that do? What if I subtract a value? What if I add a value? How does that transform my equation? That's what we're learning today, is you'll be able to see transformations in this form and apply them not only in mathematical problems, but real world problems. Number 1 here is your attendance link. So if this QR code that I had up on the screen was not working for you, just click that link right there. Again, there's instructions for if you're having any problems. We'll get to the YouTube playlist, which also is listed here. And how we're going to get graded today are these 2 assignments. One's the lesson quiz. It's over the DOLs and the bell ringers that we're about to cover. And then your homework, or in a traditional classroom, what used to be homework, is this Alex link. So that's everything you need to know. If you are not watching live, that's where you're going to get all tools and resources you need for today's lesson. So let's get going. So I encouraged those who were here from the start, after they take attendance, to work on these 2 problems and to use this Desmos link. So if you scan that link, what will come up is this right here. Let me close off some of these tabs so we're not confused at all the different things going on. Okay, what should come up is this Desmos, where these 2 questions, or excuse me, these 2 equations match these 2 equations given here. So I'm looking at number 1. This is number 1, and we're supposed to describe the continuity. And so I'm going to ask some simple basic questions. I need a senior to respond, please. A senior here. Does this look like, this graph right here, does it look like it's one continuous piece, or does it look like it's broken into multiple pieces?
Multiple pieces?
Multiple pieces. Okay, and so visually, if you're doing continuity, if you see there's multiple pieces, like I'm going to just label this one 1, this will be piece 2, this is piece 3. Whenever you see that there are 3 pieces, that means there must be at least 2 breaks. There has to be a break between 1 and 2, and there must be a break between 2 and 3. In math, when we talk about breaks, we're looking from left to right, meaning we're going off the x values. So I labeled my x-axis here, here's my y-axis. We're looking at the x-axis values. So now I need a junior to respond. When you look at this graph, which x value would be the location of the first break? Where does it look like the first break occurs? As you look on your x-axis between piece 1 and 2, what x value does it appear that the graph is broken? So I hear 1, and I agree that at x equals 1, there is a break right there. I do agree with that. However, sorry, this doesn't erase that well. That would not be what I would call the first break. That would be what I would call the second break. And I heard someone else just speak up. What was the other thing just said?
-2.
-2, very good. Let's look at a -2. So there's -1, here's -2. This value right there is where x equals -2. There is a break here. So we've found both breaks. This has a break at x equals -2 and x equals 1. Now back over on the bell ringer on what's your right side of the screen, I gave an example answer, how I would be looking for you to write your answer. It's saying like f of x has an infinite discontinuity at x equals 1. So what we've determined are the two values. What we have not determined is the type. Is it an infinite discontinuity, or what type of discontinuity is this? And so I want you to notice what you do is you look at what's happening to the graph at the spot of the break. So at x equals -2, this graph here on the left side is heading downward. Would you, full class, would you agree or disagree with that statement? The graph is heading downward on this left side of the break.
Agree.
Agree. Okay. So as x is approaching -2, and anytime we talk about the left piece, so this is the break here, this piece is on the left, this piece is on the right of -2. If you're talking about the left piece, the way that you actually label this when it comes to limits is you put a little negative symbol, like where the power be. That means the left piece. So on the left side of -2, our graph is heading downward. And the way you represent downward is by a negative infinity. So as x approaches -2, as this graph gets closer and closer to the -2 value, to this gray line, as this graph gets closer and closer to it, the y values are decreasing to negative infinity. That just means they're going downward forever. So the way you learned on lesson 1.3 to how to represent this is by a limit. And so in math, they use that little cursive L. They say LIM, which stands for limit. F of x, which represents y, is approaching negative infinity as x approaches or gets closer and closer to -2 on the left side of the graph. So that would be how you technically refer to what's happening right here. As the graph gets closer to -2, it's going down to negative infinity. Okay, now let's take a look at piece number 2 here. Would you agree with me that this piece, as we get closer and closer to -2, that this piece is getting really, really flat? Would you agree or disagree with that statement?
Agree.
Okay, I hear agree. Now I think of floors being flat. I think of walls being vertical in a room. If I'm looking around my classroom, I think of floors being flat. I think of walls being really straight or vertical. After saying that, giving that clarity, would you still call this flat?
No.
No. So I was setting you up. And so I don't think of this as being flat. So some of this is just, we need to get used to how I talk on questions I ask. I'm going to sometimes set you up with false statements. So this is not flat. So someone clarify, what would you say about this arrow? Which way, thinking of y's, would you represent this being flat, going up, or going down?
Going up.
What is that? Going up. Okay. So as x approaches -2, and again, since I'm looking on the piece that's on the right of -2, I put a little plus here. That means the right side. The y's are going up. And that's represented by positive infinity. Now, I'm going somewhere with this. You might be thinking, okay, that has nothing to do with what type. We're getting somewhere. The limit here, this is a review of lesson 1.3. The limit would be going to infinity as x approaches -2 from the right side. That's how you would actually write this as a limit. This is just kind of my shorthand to better explain what's happening. Okay, now let's talk about the type. There are 3 types of discontinuities. A graph can have infinite discontinuity. And that's when the graphs at the break head to infinities, something like that. They could have removable discontinuity. Now, removable is kind of like when you have a graph and you just have one little piece missing. Other than that, they look connected, but it's just one little open circle. And finally, you can have jump discontinuity. And that's when it's like you have a graph, and it stops somewhere, and it begins somewhere else, like you just picked up your pencil and set it down on a different location, and it continued on. Now, looking at these three types of discontinuities I drew on the right, what does our graph match? Is it going to infinities? Does it look like one little open circle, but the rest of the graph connected? Or does it look like it's jumped? What has happened at -2?
Infinite.
Infinite.
It's an infinite. Because the graph is going, the y values are going to infinities, this one negative, this one positive, it's an infinite discontinuity. And so the whole point of me taking all that time to walk through limits is, one, just to review it, and two, is to point out whenever your graph breaks and goes to infinities, you call it an infinite discontinuity. So using the sample answer for this problem, we would say, f of x has an infinite discontinuity, and I'm just going to abbreviate. I'm just going to say infinite discontinuity at x equals -2. Now, that's not the only break here. There's a second break. As I think it was Henry pointed out earlier, I have this break at 1. So using the model, what does it appear that this type of break is? Does it look like an infinite break? Do these two pieces at the x value of 1 go to infinities? Does it look like it's a removable, just one little open circle between the two? Or does it look like a jump, like the graph just picked up and moved somewhere else? What does this appear to be right here?
Jump.
It's a jump. Very good. And specifically, I'm going to label with the open circles, closed circles, using this equation. I'm going to explain it to you. This is called piecewise. The top expression represents these two pieces here. This bottom expression represents this piece over here, in piece number 3. How do I know that? It's because of the domain portions right here. This says if x is less than 1. So anything to the left of 1 came from this equation. Anything greater than or equal to 1 came from this equation. So on the right side of 1, be the bottom. Now, because this has an open circle here, I'm sorry, because this has the equal to symbol right there, that one's going to be closed, a closed dot right there. Why is it closed? Because I have the equal to sign underneath. And the way I think of this like this symbol has more ink than this symbol. So the dot's going to have more ink than that one. This one's open. Why is it open? Because it's only less than. It doesn't have the equal to. So less ink means less ink. An open circle has less ink than a closed circle. And this is a jump. So to write out this one, we would say f of x has a jump discontinuity at x equals 1. And to just complete this with limits, let's talk about the limits here. If you were going to write this as a limit, again, you'd have to write 2 limits. One for the left side of the break, one for the right side of the break, just kind of like I did here, 2 limits. And so, I'll do a different color here. This left limit, it's on the left side of 1. So it's on the left side of 1. The y's, it appears to me, it's stopping at 0. And on this piece right here, as x approaches 1 from the right side, the y is stopping at, let's count it up, it looks like a half, but notice that this is a 10 on the y-axis, which if that's a 10, that means this is an 8, this is 6, this is a 4, this is a 2. So what is halfway up to 2? What is in between 0 and 2? What number?
1.
1. So this is a jump because the y's jump from a 0 to a 1. So speaking of limits, it's an infinite break if you have infinities, whether positive or negative, it does not matter, it's irrelevant. That would be an infinite break. But if you jump from, let me write the 2 limits. So here is the left side limit. The left side, the y's go to 0. And on the right side, 1 plus, the y's go to 1. Since the values jump from 0 to 1, we call it a jump. So there's 2 breaks. And we did that all from the visual representation of the graph. Now let's look at number 2 real quick. And I'm just going to ask the class who've been here a while. I told you there was going to be 4. Was anybody able to determine where both values of the breaks occur on number 2? It's a little tricky. If you're just joining us, here's the picture of the graph. It only appears to have 1 break, but there's a second on there. Was anybody able to find it?
3 and -8.
Ashley, way to go. Ashley's saying if we look at -8, it's -1, 2, 3, 4, 5, 6, 7, 8. She said there should be 1 there. Class, do you agree or disagree with her that there's a break at -8?
Agree.
Agree. Now, if you were only using what I call your eyeball test, does it look like there's going to be a break at x equals 3? Does it look like there's going to be 1?
No.
No, but Ashley was right. There is going to be 1 right there. So let's determine what's happening. I'll go a little bit faster this time. What type of break is occurring at -8? Is it infinite, removable, or a jump?
Infinite.
Infinite, I agree, because on the left side, we're going down to -infinity as the x approaches -8. So this is the left side, so I put a minus after the -8. The y's go down to -infinity. Okay, and on the right side, here's the right side. What are the y's doing on this side?
They're approaching positive infinity.
Positive infinity, very good. Since they're approaching infinities, you would write g of x, this equation's named g of x has infinite. I don't have much space here, so I'm going to infinite discontinuity at x equals -8. Okay, now let's check out 3. Now 3 doesn't look like much, but here's one of the nice tools about Desmos. If you're on your Chromebook, you'll have to use your mouse, and it's probably a little bit harder, but if it's hard for you, I want you to look at my screen. Are you able to, on my screen, is it large enough for you to realize that I have a solid dot moving on my screen right now? Can you see that blue dot that's moving?
Yes.
Yes.
Okay, good. So watch my blue dot. And if you're on your cell phone, by the way, you just touch your screen and it'll give you that little dot as long as you're touching the graph. Watch what happens when I get to the x value of 3. So right now my x value is almost 0. There it's at 0. And I'm moving it. Watch what happens when I get to x equals 3. Now I have to be perfectly exact. So I want that dot right on the line. Watch what happens to that dot, solid dot. What happened to it?
It becomes an open circle.
It becomes an open circle. And so I want you to look on the right side of the screen. I can't move my mouse, otherwise this dot disappears. On the right side of the screen, down low, what type of break does this now resemble? Whoops, I didn't move my mouse. There we go.
It's a removable.
Does it look like an infinite? Does it look like removable or jump?
Removable.
It's a removable. That's how removable appears. So I'm just going to right click for a second because it'll freeze it. Okay, so now I can write when x equals 3, whoops, the right click went away. G of x has removable discontinuity. Fit in there, removable discontinuity at x equals +3. Okay, so all of that was done visually. I did all that only using visual. In math, if you just rely on visuals, though, it can get you in trouble. Sometimes you need to know algebra. Sometimes you need to know how to use a different type of what we call representation. So now I'm going to show you how we could have done all this using tables. So now that we know what the answers are, let me show you how you can use tables. So on Desmos, I'm going to pull out my equations again. I need to clear this off. Otherwise, it's going to all get messed up. And so right now, I had the equations showing. If I hit this little gear button, it says Edit List. And I hit that little gear button. There is this, it looks like a Microsoft Excel table right there. If you click that, it'll convert it to a table. So these values now become a table. And so if you were only going to use a table, it would become basically a guess and check. So the values that automatically show are -1, -2, 0, 1, and 2. Sorry, I got dyslexic there. Started at -2, then -1, 0, 1, and 2. And all these are the y values. Now, I want you to know these look like crazy numbers, but these places are defined because those are actual values. But if I started my list, say, at -10, and the way to do that is I'm just going to type in -10, and then I'm type in -9, -8, -7, what happened there? Let's try it again. -6, -5, -4, -3. I'm just going and showing more of a table. I already have -1, 0, 1, 2. I'm going to go all the way to 10. Okay, as you look at this list, what do you notice about -8 and 3?
They're both undefined.
Undefined. Look at the picture, what happened. So anywhere I had an x value listed, it placed a dot. That's x of -10, -9. At 8, there is no dot. Why is there no dot at -8?
Because
Has
it's
to do with that word.
undefined.
Because it's undefined. The graph doesn't exist there. So there's no dot. Now keep going. This is -7, -6. Let me close this so you can see the numbers better. -7, -6, -5, -4, 3, 2, -1, 0, 1, 2. And what happens at 3? Does it show that dot?
No.
No.
No, because it's undefined. I wish it was the site programmed it to just leave it as an open circle, but it doesn't. Instead, it just has a spot missing. That's because it's undefined. So that's a way, using tables, it at least alerts you to where they are located. We have one at -8, we have one at 3. So there, that was number 2. Let's try number 1. I'm going to take off this graph and I'm going to turn on number 1. Again, I'm going to hit that gear. I'll hit convert to table, and we have these values. At -2, sorry, I missed what you asked.
5.
No, can you just do it?
Fine.
At least put it up so I already know where everything is.
I'm gonna destroy base 2.
All right. Okay. So I'm assuming you were talking to someone else, not me. So I muted you. Looking at -2, I have a break. It says undefined. However, at 1, I want you to check this out. You got to pay attention here. If you've zoned out for a second, log back in. On our answer, we said there was a jump discontinuity at x = 1. But I want you to look at the table. Does it say undefined at x = 1?
No.
No. So jump works a little bit different. You can't rely on tables for jump because jump can still be defined there. Now, how does jump work? And this is going to be your transition to algebra. So I've shown you the graphing visual only. I've shown you then just now tables. Now let me show you how do we find these with algebra. With algebra, you do this. And I'm going to clear all this ink. I hope you have it down because I'm about to clear it. How do we find jumps with algebra? What you do, the way a jump appears is where the domain, or where you change from one expression to another in piecewise. This is the most common way to get a jump discontinuity, is piecewise. Specifically, it's where your two expressions change, the x value. So we're going to look at the x value x = 1 because that's where I switch from the top expression to the bottom one. This expression is what was graphed on the left side of the screen all the way up until 1. At 1, since it was not equal to there, it became an open circle right there, and then this one's a closed circle once again because this is equal to there. So here's how you determine if you have a jump. You plug in the x value to the expression. So if I had 2 times 1 squared minus 2 over 1 plus 2, what I'm doing is I'm plugging in the 1 to the top expression. 1 squared is 1, I'm following PEMDAS. So parentheses, exponent, 1 squared is 1, multiply times 2 is 2, subtract 2, I get 0. Bottom, 1 plus 2 is 3. What is 0 divided by 3?
Mm,
0.
0.
0. So the y value here is 0. When I plug in 1 down here, let me change colors. I have 2 minus 1 squared. Well, 1 squared is 1, so 2 minus 1 is 1. A jump occurs if these two numbers do not equal. Since 0 does not equal 1, we have a jump discontinuity. 0 does not equal 1. So it's a jump. It would not be a jump if they equaled each other. If we had 0 and 0 or 1 and 1, then it wouldn't be a jump at all. The graph would meet perfectly. Let me show you. If I change my equation just slightly, this is no longer a jump. You see how this graph connects right there? And it's not an open circle. This would be removable because now it's an open circle. That would be removable. Sorry, let me get my mouse out of the way. Let me get that point. It's so hard to get. I need to zoom in. Maybe it'll help me. There you go. Notice that's an open circle. That would be removable. This is nothing. This is continuous at x equals 1. It's not just this. It's not continuous there, but it is continuous right there now because it's a solid dot. So that's how you find jump by algebra. Is you plug in the values of a piecewise equation and you check to see if they're equal to each other or not. If they're not equal, it's a jump. If they are equal, it's not a jump. Now, what about removable and infinite? The easiest way to explain that is to go to number 2. This is where we need to factor. A removable discontinuity occurs whenever you can cancel a factor. So g of x, let me start here. I'm going to factor the denominator. And so our first lesson in the school year, we talked about how to factor trinomials. I use the terms a times c and b, where a is the number of x squareds, which in this case is 1. A equals 1. B is 5. And c is negative 24. Okay, so we have 1 times negative 24. And b is 5. I'll give you a second. I'm going to write out the list. I want you to find the two values, m and n, that multiply to be negative 24, but add to be 5. I'll give you about 15 seconds. I'm going to write out the possibilities. It could be a 1 and 24. I'm going to write out the different factors. I'm going to ignore the negative for now. Could be 2 and 12. Could be 3 and 8. Or it could be 4 and 6. Those are the only sets of numbers that can multiply to be a positive 24. Which ones of these can somehow be combined to make a 5?
8 and 3.
3 and 8. Okay, so specifically, how can 3 and 8 become 5?
Negative 3 and 8.
Okay, so 8 minus 3, I agree with that.
Yeah.
And I'd like to write it in that order because it works more with my brain. So 8 times negative 3 is negative 24. And 8 minus 3 is 5, so we found our numbers. So if you remember, that was step 2. We're supposed to look for a GCF, which I just skipped over because it did not have one. Step 3 would be you split this a power. So what do I mean? G of x is going to equal, let me leave all this, you split the a power. So instead of it being a squared, it becomes an x in the front plus the 8 that we just found, and an x over here. That x times x gives me the x squared and the minus 3. Okay, so that's what we learned how to do in the first lesson of the school year, is how to factor that. Now that I'm in this form, here's how you get a removable discontinuity. Removal occurs whenever you get this, remove a factor from the equation. So if I can remove these two, that's a removable because I removed them. So you might be thinking, how is it that it's x equals positive 3 though, when it looks like the factor that we removed was x minus 3? Well, here's how, because that's not set equal to 0. The way you would solve this is you would say 0 there, so 0 equals x minus 3. And if you do your algebra 1, you add 3 to both sides. And we find out that when x equals 3, we have a removable discontinuity. Just the same, this x plus 8 does not get removed, but it stays there forever. What is a synonym for something going forever?
Infinity.
Infinite, that's right. And so infinity represents forever. Since this one's there forever, this one's an infinite discontinuity. Since this one got removed, it is removable. So there, I just gave you 3 different ways of determining the continuity of functions. You can graph them and look at the visual. You could look at table, or you could do algebra. Now, I know that was a really long introduction, but it was very helpful, and then we're going to see this all year. And in the process, I got to review limits. I got to show you many other things. So with all that, what's happening today? What's happening that's new today? So on lesson 1.5, you're going to go over a few different things. So I had printed off these same graphs. If you wonder, what's this on my packet? That was if we were in class. That's how the Inspire would show you the graphs. I just did the equations over here, though. Let me get that equation back. Notice this one represents this graph, and this one here was the same as this graph. So that's all that is. Okay, so what are we doing today? Today we're going to look at parent functions and transformations, if you remember me saying that at the beginning of class. So the parent functions you're going to look at, there's 8 today. We'll look at the zero function, also known as constant function, a linear or identity, quadratic, cubic, square root. This calls it reciprocal. I usually call it rational. It comes from the ratio 1 over x, absolute value, and greatest integer. You'll have 8 more that appear in the second semester, or really more like December moving forward. But those are the 8 we're going to play with today. And not only going to see these graphs, we're also going to do some transformations. So here's just you'll see these in the videos. I give you some rules. But the transformations are like, what happens if I take a parabola and shift it up? And I know it's up because I'll learn I'm adding a value to the outside. What happens if I shift it down? Well, that'll be a subtraction on the outside. I can shift right. That'll be on the inside, and it's going to lie. You're going to learn the videos. It's going to be the opposite. So a negative on the inside is actually going to go right. A negative or a positive on the inside will actually move something to the left. You're going to learn about that. Then as the lesson goes on, you're going to learn that we can reflect things. So from the first quadrant to the fourth, a vertical reflection, that's outside, or a horizontal reflection, something to the right goes left. What you'll see that's consistent is if a transformation is occurring on the outside of the equation, it's always vertical. If it's on the inside, it's going to be horizontal and it's going to lie. So those are 2 rules that I skipped over right here. I told you that you're going to go over these. Call it HIVO. Horizontal is inside, vertical is out. It's an acronym. Horizontal, inside, vertical, out. And you're going to learn that horizontals, the inside lies and outside tells the truth. So something on the inside like this will lie, and it's going to be horizontal. Something on the outside will be vertical, and it'll tell the truth. So I'm just giving you a general overview. I know we have the YouTube lessons to walk you through it. And there's one more thing that can happen. We can expand or compress. Some call it stretch or shrink. I can vertically expand. I can vertically compress. I can horizontally compress or horizontally expand. It follows the same rules. If the value is on the inside, it's horizontal and lies. If it's on the outside, it's vertical and it tells the truth. So those are the transformations you're going to see today's lesson. Going all the way back to the start, this was the YouTube QR code right there. Or if you're going from your digital classroom, you would go to 1.5 and all your links are here. And this is honestly the way I'd recommend it, is whenever you click to watch those YouTubes, right here it's number 2. I'm assuming you've already taken attendance. Your number 2 thing you're responsible for out of the 4 things is if you click that YouTube playlist, you get these videos. Sorry, I don't know if you're seeing that, but okay. You have these videos. What I recommend you do at the same time is one of these optional resources. I would keep open the completed lesson packet. Here's my suggestion for how to do this lesson. So you'll walk through, and I've just done this long introduction with you. That's what I've been doing. So you don't have to watch that first video. But what you'll start on is example 1 video. And as I'm working through, I'm going to pause that. You'll see me go through all those things I was just going through real fast. And I'm going to stop here and tell you, okay, it's time for you to try 1. Here's your DOL. And so notice that this is where this video, it ends here, and I show you an open problem. Well, that open problem, if you have open the completed lesson, you could find the same spot where I work all the way through here. And on that video, this is the last thing you see me write. And then I give you this problem. What I would recommend is if you have both these open, when that video ends, switch tabs to here. On a piece of notebook paper, write down what the answer will look like. Write down for x squared, its domain, range, intercepts, all this. Why am I suggesting that? Because when you're done watching all the videos, when you've watched, you go through example 2, example 3, when you watch all those and take notes, as you go, writing down your answers, it makes number 3 very easy. So you do your lesson playlist. Number 3, you submit the answers to those bell ringers, which we already did, and the DOLs or guided practices, and the ACP type of problem, all right here. And so the ACP problem, if you're wondering, well, again, what is that? Because we haven't been in class, that's where I take those release problems of what their example problems of what the ACP might look like, and I show you, hey, here's how this will be tested. It might be tested at the end of the school year. And so that's what's listed at the very end. All of those get submitted right there. So if you've been taking notes, following, and using that completed copy, it should make you really easy because this is example 3. So after you watch the example 3 video, you have, I end right. Let me just mute that. Okay, I end right here and I say, okay, you try this one. And so if you're following along, you just come through here and you get to this problem. And now you know, okay, I got to get this answer choice. I got to figure out what the answer is. And if you struggle and you're like, I forgot what he did in that video, all you have to do is scroll up and you can see what I wrote on the same video. So that's my suggestion how to do that. That's all I have for this live section. If you have questions, this is a great time to ask me. But other than that, I'm done with new stuff. If you don't have any questions and you're ready to go, you can sign off and get working. If you do, go ahead, hang on, and ask whatever your questions are.
See you, mister.
Yeah, take care.
Have a good day.